Thank you so much, everybody, and thanks for the invite as well. I hope you're doing okay. I don't know if it's morning for Jack over there. So like I was mentioning, I will be talking about today the design and construction of a deformation measurement system we designed at CU Boulder. And starting with the intro, during the 2010-2011 Canterbury earthquake sequence in Christchurch, New Zealand, researchers found that ignoring interlayering led to an error of 50 to 91% in predicting far-field liquefaction triggering. And in this map here, we can see how the liquefaction severity number captures the behavior of observed liquefaction-induced ground failure in a number of sites, but it overestimates the amount in the southwest part of the city. Now, in empirical equations, one issue could be assessed that the line between triggering and surface manifestation is blurry. First, they use observations of manifestation, just like this picture, as ejecta to judge whether triggering has occurred in individual layers. And then the second issue is that they treat each layer in isolation, assuming it doesn't interact with anything surrounding it. In these kind of procedures, it doesn't matter if you have a sand layer in between two thin silt layers, or if there's like a really deep loose layer that's going to want to generate high excess pore pressures towards the surface. And these circumstances are not taken into account whatsoever. Now, in terms of consequences, there has been an improvement in the modern probabilistic procedures that compare to previous volumetric assumptions, but they still don't reliably consider cross-layer interaction. So these two cases show once again another example where these simplified methods could not capture the stratifications in permeability. So here we have, as an example, the CPT traces for site 33 and site 14 were similar, but the left one included a clear silt layer and thin organic seams, while site 14 has like some minor layering of silt and sand within like a more homogeneous silty to sand matrix. So even though this Christchurch database has shed some light on this, and there has been new development solutions on predicting ejecta, there's also different models coming out. There's this new movement to separate manifestation from triggering. We still lack physical models to mechanistically understand how interlayering affects the formation of ejecta and different mechanisms of deformation. So at CU, University of Colorado Boulder, we have a large centrifuge facility. And I'm going to spend the rest of this presentation just talking about the design aspects of the system and the particle image velocimetry analysis, with the goal of modeling such interlayer systems and better understand like the mechanics of the response under realistic confining pressure and shaking that the centrifuge allows us to do. So background on GeoPIV, it originated in the fluid mechanics area, and it has also been recently used to study the mechanisms of deformation in shallow foundations of uniform liquefiable layers, but with varying thicknesses like these pictures I'm showing here. Now, the approach consists of defining a region of interest within this initial reference image that we would have of the model, and then it's populated with a mesh of subsets that are of user-defined size, and then tracking them from one image to the next with displacements, and then strings can be calculated from here. This improved GeoPIV software uses normalized cross-correlation to obtain the integer pixel displacement followed by a subset displacement to sub-pixel resolution. And the current version of GeoPIV uses the reliability guided method, and it allows for each subset to deform using a shape function that describes like a first order deformation in combination with other image intensity interpolation techniques. So this new software also provides an improvement of a factor of 10 for all different deformation modes. Then the last step in this kind of analysis is the displacements are converted from pixel space to millimeters by calibrating these displacement vectors that we get against a grid of control markers that we know the location of. So in terms for the type of container that we chose was rigid because we wanted a large span of plexiglass for visualization of these interlayers. And there was a number of criteria that we followed to determine the size, such as limitations in the centrifuge platform in both plan view and the headroom space, the payload capacity of the shade table, and also to minimize boundary effects, which is an issue with rigid containers, as we probably know. And one way to address that is by using duct seal inclusions on the side walls, which has been published to help observe 65% of the incident waves energy. So in terms of the structure analysis, we designed the sections and all the details to make sure the deformations seem like the worst case scenario with the expected G level, in my case would be 70 G, and saturated sand under sustained liquefaction, so K not equaling 1, did not approach active conditions. And FEA analysis with the Abacus software were performed to evaluate the sensitivity of the container's lateral diffraction to the properties of aluminum and acrylic material when it was filled with saturated sand. So we selected a single degree of freedom structure, and the reasoning for this is because of the complexity of the soil we want to study. So we wanted the structure to be a simple linear elastic, and we had to use plane strain conditions because we want to create this two-dimensional setting so we can compare things and visualize them through the PIV analysis. The mass and the period were designed to represent a 4-story building with the consideration of having a contact pressure higher than 70 kPa and a low fundamental period to amplify those soil structure interaction effects. Now, several considerations were taken into account for the choices of the cameras, including a high frame rate to avoid signal aliasing. We wanted high impact resistance because we're talking about centrifuge testing. We wanted flexibility in memory recording and high resolution in terms of particle per pixel size ratio. We also integrated 2 GoPros, which I'm not showing in these pictures, on each side of the high speed. This will allow us to see like the whole window view that measures about 92 centimeters. And the high-speed cameras can record up to 2,000 frames per second. And the GoPros, their lenses were updated to have the same resolution in terms of millimeter to pixel ratio as the high speed. So for the lights, we had the need for powerful lighting to prevent blur in the images due to the short exposure times that are required for PIV analysis. And we also wanted like a low operating temperature to allow for more extended operational periods of times, because a lot of our centrifuge tests do incorporate silt. So those tests take much longer to complete. So now after having designed the system, we're getting ready for the actual experiments where we look at a layered system with and without soil structure interaction with stratigraphic variability, as I'm showing here, and we have the equipment to look at this physically and mechanistically understand how interlayering affects deformation of ejecta and different mechanisms of deformation. So I want to thank the GRFP program, the NSF GRFP, as well as the GAANN Fellowship. And thank you all for listening to me, and we'll take any questions now. Thank you so much.